Okay, so today's deep dive is all about tackling one of the biggest headaches in AI. I'm talking about all that critical data just locked inside visual document.
Exactly. Things like PDFs, charts, scan contracts.
Stuff that most AI systems, frankly, just can't read properly. But our sources today lay out a path to getting really accurate search with surprisingly small, commercially ready models.
And it all comes down to the problem with standard Argare retrieval augmented generation. It's fundamentally text only.
Right.
And that creates this massive reliability gap. You get these high confidence hallucinations because the key piece of info might be in a chart or a diagram, something visual.
So multimodal RA is the fix. It combines a retriever with a vision language model of VLM.
Yeah, and that VLM doesn't just see the image and read the text separately. It understands the relationship between them. That's the key to getting a grounded answer.
And the specific tools we're unpacking are two new, really compact Llama-Nemotron models built for exactly this.
It's a fascinating approach. It's this two-stage, 1 billion parameter system. First up, you have the Llama-Nemotron-Embed VL-1B V2.
Bit of a mouthful.
It is, but what it does is simple. It's a dense, single-vector embedding model. It's built for super-fast page-level retrieval.
And critically, it's compatible with basically all standard vector databases, right?
All of them. That means you're getting millisecond latency search, which is essential at enterprise scale.
Speed and compatibility are great, but the real magic usually happens in the refinement stage.
Exactly. That's where the second model comes in, the Llama-Nemotron Re-Rank VL-1B V2.
So a re-ranker.
Right. It's a cross-encoder. It takes the top few results from the embedder and then does a much deeper, more nuanced relevance check. It reorders everything so the absolute best evidence is right at the top.
Okay, but here's the question. Both of these models are small. I mean, about 1.7 billion parameters combined. Are we sacrificing real contextual understanding for speed and deployability? What's the trade-off?
That's the amazing part. The trade-off is minimal, but the benefit is massive.
Yeah.
Because they're so compact, you can run them on standard GPU resources, no huge operational costs.
And they're not just bloating the context window.
Not at all. They boost accuracy by grounding the AI on just better evidence from the start.
And that grounding, it really shows up in the numbers. Let's talk benchmarks.
For sure. If you look at recall at 5SO, finding the right page in the top 5 results, this combo hits 77.64% accuracy on tough image and text datasets.
And the re-ranker alone gives a pretty big lift.
A huge lift. We're seeing a solid 6 to 7% improvement in retrieval accuracy just by adding that second step.
You know, for an analyst who's buried in quarterly reports, that jump from around 70% over 77% isn't just a number. That's the difference between certainty and having to do a manual check.
It absolutely is. And the business case is crystal clear. You have other models like, say, Giant Re-Ranker and Zero, which performs well but has a restrictive license.
Non-commercial?
Right. The Nemotron models have a permissive commercial license. That makes them perfect for any company needing a solution they can deploy right now.
So connecting this to the real world, where are we seeing this system actually solve problems?
Well, a great example is ServiceNow. They're using this for their chat with PDF features.
Right.
The Re-Ranker helps maintain coherent conversations over these huge, dense documents.
Bringing the most relevant page forward every time.
Every single time. Then you have IBM Storage, dealing with highly technical manuals.
Lots of diagrams, I imagine.
Exactly. They treat every page as a full multimodal document. The Re-Ranker makes sure that when it finds a domain-specific term, it's in the right visual context before it even gets to the LLM. It just dramatically improves how the AI reasons over complex stuff.
So the big takeaway here seems to be that visual aura isn't just for massive experimental systems anymore.
Not at all.
We've got small, deployable models that solve this long-standing problem of ignoring visual data, and they plug right into the infrastructure companies already have.
It really just fundamentally shifts the quality of AI reasoning over complex corporate data. And it leaves you with a critical question moving forward.
Which is?
If even 1.7 billion parameter models can get this level of enterprise-ready visual understanding, how quickly will multimodal capabilities stop being a nice-to-have and just become the absolute minimum requirement for any intelligent document system you build? Something for you to think about.
Welcome to the deep dive. So I think you've probably been there before.
Oh, definitely.
You get a transcription back from a long meeting, and it's just a total mess. The words might be there, but the speaker IDs are all over the
Right,
place.
speaker 1 suddenly becomes speaker 2 halfway through. It
Mhm.
makes the whole thing almost useless for, say, meeting analytics or any kind of legal discovery.
Exactly. And that's what we're digging into today. Speaker-attributed, time-stamped transcription, or SAS for short.
Essay test is the goal. It's not just what was said, but who said it and precisely when. The problem is the way we've traditionally done this is, well, it's a mess.
So tell us why that old setup fails so badly.
It all comes down to these brittle modular pipelines. You're basically, stitching separate tools together.
Okay, so you have one system for the words, the ASR.
Right. Automatic speech recognition.
Mm.
And then you bolt on a completely separate system for speaker diarization to figure out who's talking.
And that handoff between them is the main point of failure.
It's a huge weakness. Any error in that first step just cascades to the next. And, these systems have very limited context and, frankly, a fragile long-range memory for speakers.
So it's like trying to follow a play with short-term memory loss. It forgets who speaker one was after a scene change.
That's a great way to put it. And that brings us to our source material today, which introduces MOSS Transcribe Diarize.
A new model designed to fix this.
Exactly. It's a unified multimodal large language model, an MLLM, that moves to a completely end-to-end approach.
Okay, so if those brittle modular systems are the problem, how does MOSS actually get around these long-range context failures?
The core innovation is that it's unified. MOSS does everything: word recognition, speaker attribution, timestamp prediction, all in one single forward pass.
So it gets rid of those brittle handoffs completely.
It does. And the key to making it work for long audio is a massive 128K token context window.
A 128K context window is huge, so that means it can process something like 90 minutes of audio without ever chopping it up.
No chunking whatsoever. And that's why the quality is so much better. It preserves the continuity of the conversation,
So the model has the full context.
which prevents that speaker identity drift we were talking about. The output is just incredibly clean structured segments, clear start and end times, stable speaker IDs. It even detects the language automatically.
That structural clarity is great, but let's talk performance. They tested this against some big commercial systems, right?
They did. GPT-4o, Gemini 3 Pro, 11 Labs. But before we get to the results, we have to understand how they measured success.
Okay, so we have CER, which is just character error rate, pure transcription accuracy.
Simple enough.
Yeah.
But the important one is CPCER.
CPCER.
It's a joint metric. It measures both the transcription and the speaker attribution together. So you get penalized if you have the right words, but assign them to the wrong person.
Ah, I see.
And the most important little nugget for you to track is something called delta CIPI.
Okay, delta CIPI, what's that?
It's just the difference between that joint CPCER and the simple CER. It isolates the performance drop that's caused only by speaker attribution errors.
So a lower value means you're much better at tracking who is speaking.
You got it. And MOSS consistently achieved the best performance overall.
But that smaller delta C is the real headline here, isn't it?
It really is. It's proof that having that global context just matters so much. MOSS delivered the lowest CER, CPCER, and delta C across all the benchmarks.
And these were diverse tests, long meetings, podcasts.
Even overlap-rich movie scenes, that tiny delta SPI shows a level of speaker consistency that the other systems just couldn't match.
And we should probably mention, many of those big competitors couldn't even reliably process the long-form audio benchmarks.
Right. GPT-4o and Gemini 3 Pro, they basically failed on the long tests, which really underscores the gap in what's actually deployable right now.
So MOSS is really setting a new standard for reliable, high-context essay tests at a scale that's actually useful.
It finally unifies transcription and diarization into a single model with that massive context window.
This all raises a really interesting question for you, the listener, to mull over.
It does. So MOSS gets its edge from processing the full 90 minutes, that global context. But the paper mentions future work on streaming assets.
For real-time applications.
Exactly. So the question is, how might you design a system to get the benefits of that global context and stability while still adapting it for real-time, low-latency use? That gap between deep accuracy and instant delivery is the next big challenge.
Welcome back to the deep dive. Today we are jumping straight into something that feels like a really big step forward. It's called LTX-2.
It really is. We're talking about an open source model for generating text to audio and video, T2AV.
And our mission here is to figure out why doing both at the same time is such a big deal, because we've had this silent movie problem for a while now, haven't we?
We have. You get these stunning text-to-video clips, but well, they feel lifeless. There's no sound, no atmosphere. It's an incomplete picture.
And every attempt to fix it after the fact, trying to add audio to an existing
It
video.
just falls flat. The lip sync is always off, or the Foley sounds completely disconnected.
Right?
Because you're missing the joint distribution, the relationship. LTX-2 is so promising because it generates both together, aiming for that perfect sync you see in proprietary systems. But, and this is the kicker, at a tiny fraction of the compute cost.
Okay, that's the part I want to unpack, the efficiency. The architecture is an asymmetric dual-stream transformer. It sounds complicated. Why split it? 14 billion parameters for video, 5 for audio.
It's actually the opposite of complicated. It's just smart. Video processing is incredibly heavy. It needs that big 14 billion parameter stream to handle all the visual complexity.
But audio doesn't need that much muscle.
Exactly. Audio is, informationally speaking, much less dense. So a more efficient 5 billion parameter stream is more than enough. It's a tailored approach. That's why it's so much cheaper to run.
And they talk about decoupled latent representations, so separate toolboxes for audio and video. What's the advantage there?
Flexibility for you, the user. It means you can generate a whole new audio-visual clip from scratch, or you can take a video you already have and just use LTX-2 to generate perfectly synchronized dialogue or sound effects for it.
Ah, so it's built for real-world editing workflows from the ground up.
Natively, yeah.
Okay, so that's the engine. How do they actually get the timing right? How do you make sure the sound of a footstep lands exactly when the foot hits the ground?
That's the digital blue. They link the two streams with constant bidirectional cross-attention. And to get the timing perfect, they use these very clever 1D temporal, they call them rotary positional embeddings.
Which basically acts like a
A
timestamp.
very, very precise timestamp, yes.
Yeah.
It enforces that tight alignment down to the subframe level. The timing is it's nailed on.
But what about creative control? If I want the model to be a bit more interpretive with my prompt, how do I do that without breaking that perfect sync?
That is a fantastic question. And they solved it with something called modality-aware classifier-free guidance.
Oh, okay.
Think of it like two separate dials. You have one dial, let's call it T dollar, that controls how closely the final output sticks to your text prompt.
And the second dial.
That's $18. It controls how tightly the audio and the video are forced to align with each other. So you can crank up the sync without making the model too literal about your text prompt. It gives you this incredible creative freedom.
Wow. Okay, and then there's the text pipeline. They're using this huge Gemma 3 12B encoder, but they add something called thinking tokens. What are those?
They're a way to maintain context. These tokens basically look at your whole prompt and create a kind of summary of the global context. This stops the model from drifting. If you ask for a specific voice, it ensures that voice stays phonetically accurate through the whole clip.
And the performance numbers are just wild.
Yeah.
A 19 billion parameter model that's 18 times faster than its competitors.
18 times faster than 2.2, which is video only. It's that architectural efficiency we talked about paying off. We're talking about a step time of just over 1 second versus more than 20.
And that speed lets it push out full HD 1080p video. Plus, it can generate up to 20 seconds of continuous content. That's longer than Sora 2 or Veo 3.
It's a real duration breakthrough. 20 seconds is enough for a proper scene. No more stitching together tiny clips.
So for you listening, this all means that LTX-2 is really setting a new foundation for open source T2 AV. It proves you can get state-of-the-art results without a state-of-the-art budget.
It does leave you with a fascinating question, though. For all its power, LTX-2 is still a diffusion model. Well, it lacks explicit reasoning. It's a pattern matcher.
So while the synchronization is amazing, the storytelling can sometimes falter.
Exactly. In complex scenes with multiple speakers, it can get confused about who should be talking. And beyond that 20-second mark, you start to see some temporal drift.
Which makes you wonder, without an external world model to guide the narrative, how much deeper can these systems actually go on their own?
A great question. Something to think about as you start seeing the content these next-gen models create.